तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
We have been looking at properties of dynamical systems in which you have a prescribed rule of evolution, say Hamiltonian dynamics or Lagrangian dynamics or maps, discrete time dynamics and so on, completely deterministic. You give a rule and the future is there before you. In principle, the question is whether you can solve these equations of motion explicitly or not. Numerically you could always solve them for short times and then extrapolate, but we have talked a little bit about integrability, whether you can solve these problems analytically and so on. And the general conclusion is that, for instance, for Hamiltonian systems you generally do not have a sufficient number of analytic constants of the motion in order to be able to write the solutions down explicitly. The systems are generally non-integrable. The question then arises as to how one should tackle such systems, and we saw that in the case of chaotic dynamics, for instance, the idea of an invariant density, writing down a Frobenius-Perron equation and then finding time averages written in terms of statistical averages was a very powerful way of doing things. The whole idea of statistical mechanics is precisely that. So what we should like to do now is to turn our attention to systems with a very large number of mutually interacting degrees of freedom to understand how these statistical techniques can help us to analyze the properties of such systems. I should say immediately that the subject is not a closed one. We really do not know all the possibilities that can occur when you have a very large number of degrees of freedom interacting with each other non-linearly. Many possibilities happen. Time evolutions can be exceedingly complex, very complicated, but in like most of these problems one would like to ask, are there stationary states, are there steady states, will systems asymptotically go into some steady state or the other, and if so what are these states, etc. A very important class of such steady states concerns what is called thermal equilibrium. So I am going to define what is meant by thermodynamic equilibrium or thermal equilibrium for short, and we will see how the subject of equilibrium statistical mechanics, which is now over 100 years old in this form, in its modern form, has helped us to understand systems in specific situations, specifically in thermal equilibrium and close to thermal equilibrium. So I should start by mentioning that non-equilibrium statistical mechanics is an open subject still, although a great deal is known, but equilibrium statistical mechanics is a very well developed subject, a great deal is known, and we think we understand the basic ideas behind this kind of statistical mechanics. There have been lots of efforts over the last 150 years to try to derive the postulates of equilibrium statistical mechanics from those of dynamics, from those of mechanics. This has got to do with the foundational aspects of equilibrium statistical mechanics, but the fact remains that there is no complete axiomatic derivation, and we have the reasons why this is generally not going to be possible, but the fact is one keeps trying to push the boundaries further and further and trying to understand exactly where this fundamental postulate of equilibrium statistical mechanics comes from. But right away I caution you that we need additional inputs. Statistical mechanics is not a special case of classical mechanics as yet. So you need an additional input, and this is what we will discuss and try to make plausible at some level. Now if you took the gas in this room, an ideal gas for instance, in the classical case completely non-relativistic. Even this problem, which is extremely simple, perhaps the simplest of all statistical problems, is quite complicated because time dependent questions about this system are rather hard to answer unless you have specific models. On the other hand, the equilibrium itself is rather easy to understand from the postulates of statistical mechanics, and one of our targets would be to try and understand this, to try and see where the laws of thermodynamics comes from. And to cut a long story short, I should mention that you could regard thermodynamics as the science of averages. Thermodynamics deals with average quantities, but we already have some experience in statistics, so we know that the average never tells the whole story. There is always the standard deviation, there is always the dispersion about the average, there are the higher moments and so on, and the question is, what about those, do they play a role, etc. And these are precise questions which will get some answers in what we are going to do. While thermodynamics is a science of averages, it is also a science of time scales and length scales. In fact, one could go ahead and define thermodynamics as the study of systems on their longest length scales and time scales, so that all fluctuations that happen at shorter length scales and time scales are neglected, and you look at things over very long time scales or very long length scales. This is another way of looking at thermodynamics, and therefore you can see that what I call thermodynamics for one object, one system, may be different from what I call thermodynamics for another system, just as what I call low temperature for one system could be very different from what is called low temperature for another physical system, and we will see where this comes about. So let us start with our old friend Hamiltonian dynamics. I have in mind a classical picture to start with. We have a collection of particles, for instance, interacting with each other, and let us in the beginning assume that this system is isolated from the rest of the universe completely, and you have a closed isolated system. So it exchanges no energy with the surroundings, it exchanges no matter with the surroundings, no particles go in or out, no energy goes in or out, and the system is sitting there in isolation. Now what is it we can say about it? So this is the first and simplest of systems. Here is this huge system, it contains lots of objects inside, it is kind of a completely self-contained system, sitting in isolation. Now we have to make some assumptions, so we assume that there is a Hamiltonian for this system which describes what the degrees of freedom inside are doing, so there is some kind of Hamiltonian specified with all the generalized coordinates and the momenta of the system. Okay. Now of course when you leave it alone and you assume that these rules are all time translation invariant, then we know that this Hamiltonian is a constant of the motion, and therefore this thing here has some prescribed value E, numerical value E, which I call the total energy of the system. Other than that I know very little about this system. It is just sitting there, it has got this lots of interactions going on inside, but the total energy is some E. Of course this measurement of this E requires a certain degree of precision, so I assume that there is a precision, some range delta E about which you know that the energy is E. Then the question is, what is going on inside? Very complicated stuff is going on inside. The phase space of this system is some very high dimensional phase space. If there are n particles, the phase space is 6n dimensional. On the 6n dimensional space, once you prescribe the value of this constant of the motion, you are on a hypersurface, an energy surface, and we saw that the only other things that could be constant for a very general system of this kind would be perhaps the total linear momentum of the system, the total angular momentum of the system, the center of mass coordinates, the center of mass position of the center of mass at t equal to 0. These are the constants of the motion. For a prescribed state of the motion, yeah. Pardon me? We are going to assume that this is an autonomous system, everything is given inside, that is it, this is the assumption. I start by saying that it is a collection of particles interacting with each other, no external forces are put on it, it is just kept in isolation from the rest of the universe. Then of course it is an assumption that it is a Hamiltonian system, but I do that because I need a starting point. Now I have the 10 Galilean invariants, and for a given state of motion in some given frame of reference, all these quantities like capital P, capital L and so on have some fixed values, they are all given, and the phase trajectory of the system is a point in 6n dimensional phase space, and it moves on the energy surface, and that is about all you know about this system. To specify the state of the system accurately, I have to tell you the point in phase space, I have to tell you exactly where the point is in phase space. If this is the phase space of the system, I have to say it is this point here. So that specifies all the Q's and P's at some instant of time, and then there is a very complicated trajectory going on, does not intersect itself, it is a very high dimensional object and it is wandering around here. Okay. In the absence of any further information, there is very little one can do, except our experience with normal systems tells us that this system is likely to be chaotic. It is likely to have Lyapunov exponents, some of them which are positive, and it is likely to wander around completely in a very strange fashion such that the energy surface is filled up, the system is more or less ergodic on the energy surface. This is a very mild assumption to make. It does not have to be strictly ergodic, there is a great deal of mixing, there is exponential separation and so on, but if you remember, exponential separation instability implies mixing, which implies ergodicity. So the idea is that any small volume element in phase space, given sufficient time, points from this initial volume element would come arbitrarily close to all the points of the accessible phase space. The whole phase space is not accessible to the system because I have specified its total energy. So it is only that particular energy shell or surface. If I say the energy is E, it lies between E and E plus delta E, then it is really an energy shell between E and E plus delta E, and the system lies on that, the point, representative point lies on that energy shell for all time, okay, and is ergodic on it. Okay. Then I ask the following, what more can I say? But there is very little one can say in a sense, because it is moving around in a random fashion on this energy shell, and it samples all portions of this energy shell, and we are ignorant about what happens next. And the assumption is, again based on what happens in lower dimension, which you have points occupied in this on this energy shell, is uniform, completely uniform. This says any one portion of this energy surface is as likely to be occupied or frequented as often as any other portion. This is, if you like, the principle of maximal ignorance. You know nothing about it and you say therefore all outcomes are equally likely, and this is the fundamental postulate of equilibrium statistical mechanics, which says of equilibrium statistical mechanics. This is important. I have to define equilibrium yet, and I will do so carefully, and it says in a state of thermal equilibrium, which incidentally I have not defined as yet, in a state of thermal equilibrium all the accessible microstates of an isolated system are equally probable. In a state of thermal equilibrium, many terms used here. Thermal equilibrium start with, microstates is another, accessible microstates is yet another, and equally probable is yet another. I have to define all these terms one by one, but this is the fundamental postulate, and it turns out remarkably this suffices to derive all of equilibrium statistical mechanics. Not only that, thermodynamics comes out as a special case. So the remarkable statement is that this single statement is enough and the rest follows. Now let us define all these quantities one by one. What do I mean by thermal equilibrium? Well, I mean a system which is in thermodynamic equilibrium, by which I mean the time averages of all macroscopic quantities are independent of time. The average values, the long time averages have reached some steady state, and all physical quantities which I can measure, macroscopic quantities such as total pressure, the total internal energy and so on, these quantities are all time independent, they are steady. So that is a good way to define what I mean by an equilibrium state. All physical measurable quantities, macroscopic quantities, are time independent, average values are time independent. Let us take that as an operational definition to start with. Of course you could say, if I looked at the velocity of a single particle and think always of an ideal gas or a gas, it does not have to be ideal, some kind of fluid inside which is interacting, all the molecules are interacting, it is certainly not true that if I look at the velocity of a single molecule, that is not time independent, that is undergoing collisions, it is getting forces acted on are acting on this particle from other particles, therefore that changes with time, but I would call that a microscopic quantity. It refers to an individual degree of freedom as opposed to a collection, the full average here. So if I look at the average velocity of all the particles, that is going to be 0 because this container is not going anywhere. So that is certainly 0 and remains 0 in thermal equilibrium. The total, the average momentum when averaged over all the particles, that is 0 once again. The average energy of each particle averaged over all the particles, that does not change with time either, and in this case if it is an ideal gas with no interactions except collisions, elastic collisions, it is just the kinetic energy. But even if there is an interaction, even if the particles exert forces on each other, you can still assert that some physical quantity associated with each particle is independent of time, but you have to average over all the particles. If you put in a little piece of paper in there and ask what is the average force per unit area on this piece of paper, that would be the pressure of this gas, and that would be independent of time. Okay. So such quantities would be independent of time, and I call that a state of thermal equilibrium. We will make this even more precise as we go along. Now if the average values are independent of time and the averages are taken with respect to some probability distribution, the only way this can happen is if the probability distribution is itself independent of time, because that way you are sure that all the moments of all the variables you take are all independent of time. So this is equivalent to saying that the probability distribution itself, such as it is, of whatever we have to specify, is independent of time completely. The next thing that we have to ask is what is meant by a microstate of the system. And I am going to give some simple examples of microstates and macrostates. By a microstate I mean specifying the state of every constituent of the system. If it is a collection of molecules, then it is equivalent to telling you what is this molecule doing and what is that doing, what is this doing, and so on. Since we are talking about classical particles, the variables that you use to describe each particle would be its generalized coordinates and generalized momenta. Now if I tell you the generalized coordinates and generalized momenta for each and every particle, I would call that a microstate of the system. On the other hand, if I tell you the total momentum at any instant of time of all the particles, I would call that a macrostate, a descriptor of a macrostate of the particle. We will come across examples of microstates. I am going to give a simple probabilistic example of microstates. What do I mean by accessible microstates? Well, suppose the range of energy that each particle can take runs from 0 to infinity, the kinetic energy can run from 0 to infinity. It is clear that if you have specified the total energy of the system as capital E, some finite number, a given particle cannot have an energy larger than that, a kinetic energy larger than that. If you do not have any potential in the problem, but just the sum of kinetic energies is the total energy, it is evident that if you give me a total energy E, no individual particle can have an energy larger than that. Therefore, some microstates are not accessible anymore to the system. So what I mean by accessible microstates is all those microstates which are compatible with whatever conditions you put on the entire system. The rest are not accessible to you. If you increase the capital E, obviously more states become accessible. If you decrease the capital E towards 0, it is clear almost all the particles must now get to rest, because any one of them zipping very fast will exceed the total energy. So it is going to give us a concept of the density of states, because it's going to,
in that condition, one particle having all the energy and
yeah,
rest all being zero, that is also an accessible microstate.
that could be an accessible microstate, absolutely.
This is saying that is also that has the same probability as all particles.
Yes, indeed, indeed it is saying that, and you will see what is happening, you will see why that is not going to happen in practice. That is exactly right. In fact, his point is, suppose you have a collection of 1,000,000 particles and the total energy is 1 joule, say, or 10 joules. There is a possibility that instantaneously you might look at the system and discover that one particular particle has almost all the energy, close to 10 joules, and the rest of it has almost 0 energy. This too is an accessible microstate, definitely, and that postulate of equal probability says that this is perhaps as equally probable as anything else. That is true, that is true, that is necessary, as you will see. This is certainly going to happen, but I hope the idea of an accessible microstate is clear. It will become clearer as we go along. So to repeat, a microstate of a system, which I have to precisely define more carefully for a specific system, is telling you what the state of each microscopic constituent of the system is, and a macrostate is giving you some gross information, some overall information about the system. And the statement here is that in a state of thermal equilibrium, which we have defined by for operationally as a state in which all macroscopic quantities have time independent averages, in that state all the accessible microstates of the system are equally probable. This is a postulate. You could ask, can I derive this? Can I derive this from mechanics? Well, it turns out that what you can derive is the converse of it. You can show that if at any instant of time all the microstates of a system, accessible microstates of a system, are equally probable, if you can prove that, then you can show it remains so for all time, and if it remains so for all time, it means the system is in equilibrium, all averages become time independent. Unfortunately, from mechanics or dynamics you can only prove the converse of what you want, whereas what we have is a situation where you have thermal equilibrium and you are trying to ask what is the probability distribution. You are trying to work backwards. You have all the average quantities and you discover they are all time independent, and you say, oh, so I am in thermal equilibrium, but what is the probability distribution that could lead to this? There is no way of deriving it. You make a postulate, but you can go the other way. If you give me information about the probability distribution, then I can go back and say, oh, all the microstates are equally probable, implies that they remain so for all time. And what does that imply? We know already what this means. We have talked a little bit about densities and so on, probability densities, etc. Remember that in phase space the probability density obeys an equation of the form H rho. This is the Liouville equation which I mentioned on an earlier occasion in the Hamiltonian dynamics, classical Hamiltonian dynamics. It says that the phase space density of the system obeys a partial differential equation. Delta rho over delta t is the Poisson bracket of the Hamiltonian of the system with rho. If this distribution, probability distribution, is independent of time, it implies this must be equal to 0 in equilibrium. So for the equilibrium distribution this is 0, so you have a situation like this. Now what does this imply? What does it imply for rho? It is a constant of the motion, so what can it depend on? It is not an observable, it is not a physical observable. Probability distributions are not physical observables. Average values, mean square values, moments of physical observables, of physical variables are observables, measurables, but a probability distribution is not a measurable by itself. What does this imply? Remember that we also found that for any physical quantity df over dt was fh plus delta f over delta t. If there is no explicit time dependence, that goes away, and then this was the equation of motion for any quantity f which is a function of the phase space variables, the p's and q's, and if it is a constant of the motion, then it Poisson commutes with the Hamiltonian. Otherwise this is the equation of motion, but that is different from the equation of motion for the density, because the phase space density itself, the probability density itself, obeys an equation which has a minus sign compared to that equation here. This is very important, this minus sign. This immediately tells you that a probability distribution, a phase space density, is not a physical observable. It is what you need in order to calculate average values of physical observables. So this says that if it is 0, if delta rho over delta t is 0, it says rho equilibrium must be a function of h and possibly the other constants of the motion, possibly the other constants of the motion. And what is it we are saying now? We are saying that for a given system, for a given state of motion in which all the P, capital L and so on are all fixed in some frame of reference, it is only the Hamiltonian now that you are worried about, and that Hamiltonian has a value E, numerical value E. Therefore you can immediately conclude that under this condition, under these conditions, for a closed isolated system in thermal equilibrium, this equation tells you immediately that rho is rho of h equal to, and what can it be on the right hand side? You are on the energy shell, so the Hamiltonian has the numerical value E, and that is all you know about it. It should be, so h must be equal to E. So what function would you have for the probability density? What possible function could you have? Yes? Yes? What function of h can it possibly be? You are on the energy shell, so remember h is constrained to be equal to E numerically, a Dirac delta function, nothing else is possible. That is it. So in fact we found the equilibrium density, and now if you take this energy shell and partition it into little cells, this thing does not distinguish between one cell and another, and therefore it is clear immediately that this is true. If this is your energy shell, the probability of being here or here or here, any equal sized element, is exactly the same. A statistical ensemble with that probability distribution in phase space, which corresponds to an isolated system in thermal equilibrium, has a special name. This is called the, what is the name given to this ensemble? Because it says something about microstates. It is saying something about each microstate now, it is saying they are all equally probable. What would this correspond to? What would you call this? This is called the micro it is called the microcanonical ensemble. Having told you that the microcanonical ensemble has this very singular probability density, just a delta function on the energy shell, on a given energy shell, you still have to come to terms with what does this mean, how do I classify states, and so on and so forth. That is the next task, to see what are we going to do about it, how are we going to use that information. Okay. But the fact is we run into a problem right away, and the problem is, if this is phase space and I have to specify a particular point on this phase space in order to tell you a state of the system, that is in 6n dimensional phase space, the probability of a single point, it is a set of measure 0, the probability in a continuum of finding any particular specific value, sharp value, is 0. and the number of microstates is infinite, because the number of points is uncountably infinite in this phase space. So you right away run into a difficulty. We don't know how to translate that into specific prescriptions for finding probabilities of microstates, because the number of points is infinite straight away, and therefore you need to now make a further assumption, and that is that you have some finite resolution, that we cannot specify a point in phase space, we do not have infinite precision available to us. If I do that right away, if I say this is the smallest area or volume element in phase space that I can specify, then you are in good shape, because as long as that little element is finite, no matter how big this phase space is, you can always count the number of cells in phase space that you have. So it is the total phase space volume divided by the volume of a cell, that is equal to the total number of states or microstates. So the possibility of the uncountable number of points that you have in a continuous space has been tamed by saying I have discretized it, I give you a resolution, and I will now define the phase space, the microstate, as something that is inside an elementary volume element in phase space. Now of course if this is where it ended, you would still have operational difficulties. You would have to ask, where does this resolution come from, where does this finite resolution come from? In principle, if I make my measurement better and better and better, then I should be able to get over this, and then what would happen in the limit? It would still lead to this problem that you have an uncountable infinity of states. Fortunately for us, Providence is very kind to us and has given us a finite resolution by Planck's constant. So we know that there is Planck's constant, that nature is quantum mechanical, and while we are playing all these games classically, we know that in principle at the ultimate level there is quantum uncertainty, and definitely you cannot specify the p and a q of a particle, conjugate pair of variables, to better than Planck's constant precision. So the uncertainty principle comes to our help. You could give a whole theory of classical statistical mechanics pretending that there is a finite resolution, but the cause of this finite resolution lies in quantum mechanics. It is exactly the same as saying that effectively I could do rigid body dynamics, but classically you cannot explain the rigidity of matter. You finally have to take recourse to the fact that it is a Pauli exclusion principle that makes solids impenetrable. But of course when you are trying to find out what the stress or what the yield stress or the Young's modulus of a piece of metal is, you do not need to go to the Pauli exclusion principle. We use the fact that that has made matter rigid and then use an operational effective theory. In exactly the same way, all of classical statistical mechanics is going to be predicated on the assumption that there exists a resolution, ultimate resolution, and the interesting thing will be, you will see that it appears in such a form that as far as thermodynamic quantities are concerned, the actual precise size of this volume element is irrelevant, because all physical things become independent of that to a certain extent. There are other places where it would appear, and if you go to the regime where you have for instance lower and lower temperatures, then quantum effects would start playing a role and you can't make these assumptions, and that of course classical statistics would fail in that case. But we will see carefully in what regime it plays a role and where it applies. Yeah.
So Planck's constant is itself like a postulate.
Is like a?
Like Planck postulated that there is a constant edge.
Yeah, we have no doubt at all that this constant exists, and we have no doubt at all now. Of course it is finally based on experiment over the last 100 odd years. So we know that there exists a quantum of action, we know that Planck's constant exists, we know the uncertainty principle is valid, we know that quantum mechanics is valid in its present form. So that is a given, that is an assumption. So we are far away from Planck's postulate of energy quanta being energy radiation coming in quanta and so on. We are far away from that. We know now based on 100 years of experience and direct physical observation that Planck's constant exists and provides a fundamental limitation on the specification of p's and q's, conjugate pairs of p's and q's. So we take that as given. Okay. That immediately implies this little relation delta q delta p is greater than or equal to h cross over 2. This immediately implies that in this phase space for every conjugate pair of q's and p's you have a little resolution problem there, and you can only write the value of these q's and p's to within a little area whose value, whose magnitude is some constant times Planck's constant, h over 2 pi or square root of 3 times h, it does not matter, something proportional to Planck's constant. And therefore in this full phase space, 6n dimensional phase space, the small volume element that you are talking about is ultimately proportional to h to the power 3n. There is an h for each q and p, and for 3 of them, and for a single particle there is an h cubed, and there are n of them. So this volume element is got dimension, the volume element is 6n dimensional, and therefore the little thing here is of size h to the power 3n, whatever it be. Okay. So we keep that at the back of our minds here. Then if this full phase space has volume omega, let me not use omega here, let me call the full phase space volume of phase space equal to some, I do not want to use capital V because I am going to use that for the physical volume in configuration space for systems. So let me call this volume of phase space, for want of a better word let me just call it M, capital M, it is very bad notation but bear with me for a minute, we do not need this. Then the number of microstates is equal to M divided by h to the 3, and let me call that omega. And that is a countable number, and for a finite M this is finite because h is now a non-zero quantity, and therefore this number here is some finite number, very large number of microstates. Okay. Then the fact that your density is simply saying that h is equal to E and nothing more implies that each of these microstates on this energy shell has as much weight as anything else, and therefore what is the probability? Once I have said the microstates are all countable, then what is the probability if each of them is equally probable? It is just 1 over capital omega. So
what's the volume of the energy shell?
pardon me?
M is the volume of the energy shell.
M is the volume of the energy shell, that is right, and then the number of microstates is omega, and as he points out, just a minute, as he points out, this M is therefore a function of E, because you have a different E you might have a different total volume of this energy shell, and therefore this is omega of E, and that is 1 over omega of E, that will become relevant. Yeah.
So you said that volume of each cell is proportional to h power 3n.
Yes.
But how can we assert that the number of states is equal to h power?
Well, it could be 3 times h power h to the 3n, it could be square root of 7 times, we do not know a numerical value here. So all the equations I write down are modulo some numerical factor here, some factor. Obviously if I want to specify this state more and more accurately, I try to make it as best as I can. I would not choose something which is 10 to the 100 times Planck's constant, then of course you lose information. So you would like to refine it as much as you can, but the point I am making is there is an intrinsic fundamental limitation to how accurate you can be, and incidentally we will talk a little bit about it in perhaps quantum mechanics course. This uncertainty, this limitation has absolutely nothing to do with measurement, it has nothing to do with your inability to measure or the fact that your apparatus is not good enough or anything. It is just that for quantum mechanical objects you cannot define momentum and position, conjugate momentum and position with infinite precision at the same time. Simultaneously you cannot define a state of such a system, a quantum system, in which both the position and the conjugate momentum have arbitrarily precise values. It is not possible. You might even say the property does not exist. Now that is semantics now, but you might even say that. You might say that an electron does not have the property of a precise momentum and position in any given state, the electron. So it is a fundamental limitation, and we are using it in a very crude way here. We are simply saying, okay, it finally amounts to saying there is some kind of uncertainty, and let me just say that that gives you a resolution in phase space and enables me to start counting the number of microstates. And the first thing we realize is that the probability is 1 over the total number, and that is normalized to unity because you sum over all these guys and you get 1. Now having said this much, let us now take a break from this and look at a system, a very trivial system for a few minutes, where the idea of microstates and macrostates becomes very clear. It is actually easy to write down, and once it is easy to write down in that system, then we can come back here. But this is a little more complicated because the microstates of a single particle, the particular state of a single particle itself is a very large number of possibilities, whereas we would like to look at a toy model where each constituent can have only a countable number of states, like 2 or 3 or something like that. Then it gives focuses our ideas better on what I mean by microstates and macrostates. So let us do that. And the system I am going to look at, this is it is a toy model, that is going to be my system, and this is just a set of coins. I just take a set of coins, n coins, capital N coins, and each coin has 2 possible states. I assume that it is either a heads or a tails. You can use this paradigm for various other things, so it is n identical coins, but identifiable coins, that is important here. I would like to say that I have coin 1 here, coin 2 here, coin 3 there, and so on, and each coin has 2 possible states, either a head or a tail, and I will denote them by H and T. I put these guys together after a coin toss experiment and I discover I have something like this. Something like this. So I have a string of T's and H's, n letters. Okay. That is a possible string. Okay. I call this a microstate of the system, because it says something about each constituent. And I jumble up these H's and T's, I have another microstate of the system. So this is my set of microstates, this is a microstate. Just a matter of caution, you must not imagine that a microstate is a state of a given constituent. It is still a state of the entire system, but it is a state which specifies at microscopic detail what is happening to every constituent, and that is why it is called a microstate. But it is still a state of the system as a whole, because I have told you the state of all the coins in the system. How many microstates does this system have? It has 2 to the power n microstates. So you see, we have right away been able to count 2 to the n microstates. Let us make life a little simple and assume that there is no bias in any of these coins, so that in a given coin toss the H and T appear with equal probability. If there is a bias, we can allow for that, it would mean some weights and so on, but to start with you have 2 to the n microstates of the system. Okay. Now what would you call a macrostate of the system? A given number of heads. So after I do this experiment, I lay them all out, I count all the H's and I count all the T's, and of course there is a constraint on this system. So this says that total number of equal to H and total number of tails equal to T. So let us call n is equal to H plus T, of course, total number of heads plus the number of tails, and for a given capital N and capital H I have specified a macro state of the system, because capital T is known immediately. If capital N itself is variable, then I have to tell you what is capital N and capital H or capital T, does not matter. It is sometimes convenient to do the following. Let us also define, I am sorry I used M there, I do not want to use M there, let me call this something else. Let me call this some curly M. This is why we must all practice writing Gothic script so that we can add more symbols to it or some other script. Okay. So let me call capital M for reasons which will become clear later on. I want to use this for magnetization, that is why I put a capital M here. Let me call this the number of heads minus the number of tails, the difference between the number of heads and the number of tails. Okay. Then a specification of the pair of numbers capital N capital M is equal to telling me a macrostate of the system. Yeah, N M or N H or H T. A macrostate of the system as opposed to a microstate. Okay. Okay. How many possible macrostates are there for a given capital N? For a given capital N, how many possible? Well, let's look at it this way. For a given capital N, the number of macrostates what is the least value of capital H and what is the largest value? So how many macrostates are there? N plus 1. So the number of macrostates is N plus 1. And the number of microstates is much larger, exponentially so. This is e to the n log 2 and that guy is linear in n. So the number of microstates really is exploding, as you can see, but the number of macrostates is going much more leisurely, it is just going like n in this fashion. It is like the number of degrees of freedom in the system, but this is going exponentially in the number of degrees of freedom, and that is going to give us an important lesson. Now if the coin is unbiased, what is the probability that I get any particular microstate? 1 over 2 to the n. So it is a small probability, it is a vanishingly small probability. The probability of a given microstate is going to be vanishingly small because it is 1 over 2 to the power n. But what is the probability of a given macrostate? It depends on the macrostate. So what is the probability? Now let us ask this question here. So I have 0 less than equal to h less than equal to n, and I ask what is the probability of h? What is this equal to? Well, it is easy to see this because I must have a capital H number of little h's in that string, and the probability of any one of them is a half. So this is 1 over 2 to the power h I must have here, that is very clear, and then the rest of them must be tails, and the probability of that is 1 over 2 to the n minus h, because these are independent, these coins are independent of each other, and therefore the probability of 2 of them being heads is 1 over 2 squared and cubed and so on, and you require capital H of them. So therefore this is the probability, but now comes the important fact that I do not care in which order the heads appear, I do not care at all. I am just counting a macrostate, I am looking at a macrostate, I am not interested in the particular sequence, and therefore this is now multiplied by n c. This is the number of alternative ways in which you can achieve that. This, by the way, is this many heads and that many tails, so it is multiplied, because the real meaning of the word and is multiplication of probabilities, and the meaning of or is addition of probabilities. So you can have it this way or that way or that way, and you add up all those probabilities, and then the answer is this is the number, the combinatorial factor, which tells you in how many ways you can have capital H little h's in a string of length n of h's and t's. So that is the probability distribution. What would you call this probability distribution? It is called the binomial distribution, and incidentally in this particular problem this factor cancels against that. But if this were not the case and you had a biased coin, such that the probability of a little h, probability of h equal to p, probability of tail equal to 1 minus p equal to q, then again I am sorry to use p's and q's, these are not positions and momenta, these are probabilities here. What would this become? This would become, instead of this you would have a p to the power h, and this would be the power q to the n minus h. And since this guy looks like a term in a binomial expansion of p plus q raised to the power n summed over h, this is called the binomial distribution. Incidentally, it is obvious that summation h equal to 0 up to n p of h here, in the most general case here, this guy is equal to p plus q to the power n, that is equal to 1. It immediately follows that the total probability has to be 1, because it says the total number of heads must be either 0 or 1 or 2 etc. up to n, and that of course is normalized automatically. And a given p of h is the coefficient of little p to the h in this expansion. So in fact if I put a generating function here, if I put x to the power h, then this would become p times x plus q to the power n, and that is the generating function for the binomial distribution. As you know, for any probability distribution, the quick way to find all the moments of this distribution is to define what is called the generating function for this distribution, and then the operation of finding averages, higher moments, reduces to differentiating this generating function and then setting x equal to 1. So the generating function for this guy, since I am going to use generating functions, let us for the moment take biased coins and say that the probability of a head for each coin is little p and tail is q. Otherwise of course p and q become equal and things come out, things become look a little easier, but it is good to keep the general case in mind. So this is what the generating function is. P of h is therefore the coefficient of x to the power h in the binomial expansion of this generating function. What is the first property this generating function obeys? F of 1 is equal to 1. You put p equal x equal to 1, then of course it simply says the total probability is conserved, it is 1. What is the average number of heads? What is the average number of heads? And how do you define the average number? So let us define the average here. The average equal to summation h p of h divided by summation p of h 0 to n. That is the definition, that is the very definition of the average number of heads. But what is that equal to? We know that the denominator is already 1, so we do not need this. And how do you find the numerator? You go back here to this expression here and you differentiate with respect to x, and if you do that you get an h coming out here and then x to the power h minus 1, and then you put x equal to 1 and you get hp of h. So this is also equal to f prime of 1. That is the great advantage of using generating functions, because finding averages becomes trivial. Now what is this equal to? I differentiate this, you see the left hand side is given by this, but that is equal to this guy here, differentiate it and set x set equal to 1, but I can also differentiate the right hand side and set x equal to 1. If I do that I get an n coming here, px plus q to the n minus 1 multiplied by p, and I put x equal to 1, px plus q becomes p plus q, which is 1, and therefore this is equal to np. Right? You must always check that if little p is 0, the average number of heads must be 0. If little p is 1, then the average number is the number of tosses itself, capital N, and indeed we know that if the coin is fair, then on the average half of them are going to be heads, so you get n over 2. Therefore this is completely checks out. This is what the average number of heads is. What is the mean square deviation? What is the mean square value? What is the standard deviation? Well, we need to find h squared, so let us do that. H squared is easily found. Well, if I differentiate this twice, what do I get? F double prime of 1 is equal to what? I differentiate it twice, I get an h times an h minus 1, then I put x equal to 1, so it is the average value of h times h minus 1, but that is the same as the average value of h squared minus the average value of h. But if I differentiate this twice, I get an n times p, and the second time I differentiate I get an n minus 1 times p. So this is also equal to n times n minus 1 p squared, and that is equal to this quantity here. Therefore h squared equal to n squared p squared minus n p squared plus the average value of h, which is np. We already know that, and therefore what is the standard deviation or the variance? The variance of h equal to h squared minus h average squared, that is equal to the average of h minus average h whole squared. As you know, the variance of a random variable is the mean square minus the square of the mean, but that is the same as saying it is the mean value of the square of the deviation of the variable from its mean value, and that is a non-zero quantity, that is a positive quantity unless it is a sure variable. So this thing here turns out to be equal to n squared p squared minus np squared plus np minus n squared p squared, because the average is np, and if I square it I get this, and this term obligingly cancels out, and this is n times np times 1 minus p. So it tells us that while the average was this, h minus h whole squared equal to np times 1 minus p equal to npq. Q is 1 minus p. Therefore, what is the standard deviation? Square root of this guy. So it says delta H equal to standard deviation equal to square root of npq. If you like, that is the uncertainty. If you define the uncertainty as just the standard deviation, it is equal to square root of npq. For a fair coin, p and q are halves, so there is no problem there. npq is just square root of n over 2. On the other hand, what we would like to find out is what is the dispersion about the mean. Therefore, the relative fluctuation equal to delta H over the average value, and this is equal to square root of npq divided by np. This is equal to 1 over square root of n square root of q over p. So the fluctuation about the mean value divided by the mean value tells you the relative scatter, and that quantity is proportional to 1 over the square root of n times square root of q over p, and for an unbiased coin that factor cancels out. So the important thing is this factor. It says the relative fluctuation is becoming smaller and smaller when the number of coin tosses becomes larger and larger. If the number of coin tosses is 1000, this guy here is already of or 10,000, it is already 1%, 1 over 100. If it is 10 to the 23 or 10 to the 24, it is 1 part in a trillion. So it says the fluctuations about the mean are really 1 part in a trillion, and that is what is going to happen in thermodynamics. Under equilibrium conditions, it will indeed turn out to be this. It will indeed turn out to go like 1 over square root of n, which is very characteristic of all these distributions, and this is what is going to eventually win the day. This is why thermodynamics works. We will see that. But going back there, you can see that you can find all the moments once you have the generating function, which is really the crucial point. How do you find the generating function? The word for the generating function in statistical mechanics is called the partition function. It is really finally just a generating function. You can call it a Laplace transform, a green function, you can propagate, you can call it by many names, but it is really just a generating function finally. It is going to tell you how to calculate average values. It is not as trivially defined as in this case, little less trivially defined I should say, and the measure need not be uniform and so on and so forth, but the rest is detail, a matter of detail. What we must do, and that is going to be done next time immediately, is to ask why it is that it is more probable to have 50 heads and 50 tails in 100 coin tosses than 1 head and 99 tails, and the reason is buried in the combinatorial factor NCH. Every sequence is equally probable, but that sequence or that macro state will dominate which has the largest number of contributing microstates, and that is how the world works. That is it. So although intrinsically it is possible that there is a microstate in which one particle carries all the energy and all the others carry no energy in a large system, that microstate is no more probable than any other microstate. But if you ask what is the most probable macrostate, this has contribution from maybe 1 or 2 microstates, whereas other states would have contributions from a very large number of microstates. So that is what is going to happen, overwhelmingly so. Even in this coin example you will say you will see that NCH, if n is 100, 100C50 is going to be exponentially larger than 100C1, and that is why statistics works. So all this is contingent on how large is large, and that of course looks like a question which can't be answered, but we could ask how large is large compared to 1 if it is integers. How large is large? What would you say is large? Now we got to be a little more precise, and fortunately for us there is a definite theorem. This is called the central limit theorem, and it is there is a very powerful formula called Stirling's formula which will tell us how large is large, and you will see indeed that fairly small numbers are quite large for these purposes. 100 is already very large, 10 to the 24 is inconceivably so, and that is why this whole business works. So it looks like these large numbers have a life of their own, and it really is so. We will make it precise.